Welcome to our first video for our statistics unit. In this video, we are going to look at gathering and organizing data and visualizing data. For 8.1, we have 3 learning objectives. So we're going to look at different sampling techniques, and then we're going to look at the appropriate ways to organize data, and then also look at frequency distributions for a couple of different types of data. So let's first talk about our building blocks, if you will, for our statistics unit. And that is going to really be where the data is coming from. And that is our sample. So when you want to first start coming up with some kind of a study that you're going to do or some kind of investigation that you're going to do, you need to come up with how you're going to get that data and the people that you're going to talk to. And wherever you're getting that data from, that is called your sample. So if you want to poll people about an upcoming election, then you would come up with your survey questions, and then you would pick people that you're going to talk to. And those people make up your sample. Now, there's lots of different ways that you can make that sample, but the sample is where you get the data from. So the people make up the sample, and the answer to their questions is the data that you get. So the sample is the group of things that you're getting the data from. The thing that you are going to get the data from could be people if you're talking to people, but you could be running some kind of experiment. It could be plants, it could be animals, it could be anything like that. The data that you collect could be any kind of unit. We're going to look at primarily numerical stuff, but it could be labels, what we're going to call qualitative or categorical data, where it's just words, like when you ask people like, what's your favorite ice cream or something like that. Now, we're not going to talk to everybody that you could possibly talk to for a scenario. Like if you're going to stay with this election idea, you can't talk to every single person that's going to vote, right? You don't have time for that. You're only going to talk to some of those people. So some is for the sample. If you were going to talk to everybody, then that would be the population. The population is the everything. So anybody that could be asked, that is going to be your population. The people you actually do talk to, that's going to be the sample. Now, the way you get the sample really matters, because if you don't get a sample that is representative of your overall population, the data that you get may not be accurate. And so this is a pretty famous one. It's a little old now because it's from 1936, but there was, long, long ago, they did a poll for Literary Digest, which I believe is the old Reader's Digest, which is also, I think, gone now, but that doesn't really matter. They did a poll, and they said, well, who do you think's going to win? Franklin Delano Roosevelt or this person, Alfie Landon? And in the poll, they came out with that 61% of their readers were going to vote for this Alf Landon. Well, clearly that didn't work out because FDR was definitely our president. Nobody knows who Alf Landon is. So that's a great example of getting a biased sample. They only talk to the people who are reading their literary magazine. Right? So it was just one type of person from our overall population. And that subsample, it is a sample, but it wasn't a sample that was representative of the overall population. So we got a couple of different ways that we can get a good sample that would be representative of our overall population. There's the simple random sample, which is kind of like normally the best way to do things. When you hear about scientific experiments, that's usually the one that you're hearing about. But there are other ones that are also ways that you can get a unbiased sample. A systematic random sample kind of takes the idea from the simple random, but then randomizes also itself where you're going to start in the list. And then you kind of have a method from there. So it may tell you, oh, start at line number 465, but then take every 100th one or 10th one or something like that. Then there's stratified sample, where you're going to break things up into groups and then take a little bit from each group. And then there's a cluster sample, where you break it up into groups, but then you take whole big chunks. So let's look at each one individually. So the simple random sample is kind of the old storyline where you put everybody's name in a hat and then you pull out 5 names from the hat. That is a simple random sample, and a lot of times we will just go ahead and talk about these as being a SRS. So now be careful if you Google random sample as opposed to simple random sample. There really is a difference between the two. For us, we're not going to worry about that. What we're really interested in is as first bullet points. Basically, every single person in the population has the same probability of being selected. So if I wanted to survey students at Mitchell Community College, I would go to the database that has all of the names in the list, and I would say, hey, random number generator, generate me 100 different student IDs to sample. And everybody would have the same probability of being selected. Or if you watch, anybody in your household plays like the Lotto or the Pick Six or something like that, they got the little ping pong balls floating around. All the little ping pong balls are the same size. The number, each number is only on the ping pong ball once, and then, so each one of those has the same probability of being selected. We don't do a whole lot of like papers and hats anymore. Usually now we have random number generators, so that will pick from a list or something like that. Kind of to put a little bit of a method to that madness is a systematic sample where you have everything lined up. So you have your everything in a list or organized in some way, and it says, hey, I'm going to randomize some starting point. Let's go ahead and say the third. And then I'm going to take every kth or nth or something like that. So, hey, go ahead and start at like number 3 and then take the third of every one. Or you can say start at number 1 and take every fifth. So this one and then 1, 2, 3, 4, 5. 1, 2, 3, 4, and then this would be like your 10th car, right? And then you would take that one. So still, it's pulling from the everyone. Everyone sort of has the same probability of being selected, but it's really going to matter where you fall in that sampling line, because if you start at 2 and you want to take every third one, well, there's no way to get number 3. Those are the two types of samples when everything's kind of in one big long list. Sometimes we want to divide it up. And so if you're talking about groups, you're talking about either a stratified sample or a cluster. What a stratified does is it breaks that sample that you want to look at, your population, into at least 2 different groups. So you could say men and women. If you're talking about like a high school, you can say freshmen, sophomores, juniors, seniors, right? Something like that. Then you break them up into groups and you say, oh, I'm going to take, 3 from each one, or I'm going to talk to 10% of these groups and then 30% from these groups, where you're going to break everybody up into groups and then take some from each group. How you pick that sum, is it the same amount from each, or is it a percentage? That kind of just depends on what method that you're going to use. Stratified often will pick for, like, let's say with the freshmen, sophomore, junior, seniors, right? But let's say that out of 100 students, 20 are seniors, 30, and then let's say 40 are, and then you only have 10 sophomores somehow, right? So if you wanted to take a group, maybe you're only going to do like 4, 1, 3, and 2, right? So you can take 10% of each one of these, so that it kind of keeps the weighting of how that population is distributed. Or you can just say, I'm going to talk to 2 from each group, and it doesn't matter how many people are actually in that group. The important idea is that you're going to draw a sample from each stratum, right? So let me get this ink out of here, and this is the big deal. You're going to take some from each little group. Where with a cluster sample, you break it up into groups and then you take big chunks. So I take this population area, I put it into clusters. So you can see I have all my different precincts here, and I broke it up until, I don't know what it looks like, 32 different precincts. But I'm not going to, if it was a stratified, I would say, oh, I'll talk to like 3 people in each precinct. But maybe I don't want to be walking around. Maybe I only have 3 people to do my interviews. And I say, hey, interviewer number 1, you go to 16, 2, you go to 5. My last person, you go to 28, and just talk to people in there. So these other ones, nobody gets represented from in there. That's the difference. So for stratified, you have all these different groups, and you get a couple from each group. Maybe it's the same amount, maybe it's not. That doesn't really matter. What matters is there's groups, and you're talking to at least 1 person in each group. With a cluster, you have groups, but there's entire groups that you don't talk to. You just talk to everybody here and everybody there. Those are called probability samplings. So it's based upon some kind of mathematical way of doing things. There's also what's called a convenience sampling, which is basically just no rhyme or reason to it whatsoever. So you just go somewhere, you set up camp, and people are walking by, and you ask them questions. It is election season. You will see people just standing outside of like Walmart or wherever, the supermarket, Publix, and they want to ask you questions. That's a convenience sampling. You had every intention on being there. It is convenient for them to just stand in one place and see who shows up. It's not random because you chose to go there. You knew you were going there. It's random for the person who's asking. They didn't know you were coming, but you had every intention of going to Starbucks that day. So let's look at a couple of these, and you can pull up the PowerPoint or pause the slide to see if you can name any of these. Maybe we'll look at number 1. Research team wants to study demographics for college students in the U.S., and they take a proportionate sample of students and majors reflecting the actual U.S. percentage. So they're going to break people up to majors, and they're going to talk to some people in each major. So we got a group, so we're talking about a stratified or a cluster. But I'm talking to some people in each major, so that's going to be a stratified. Let me see, this last one, the difference is an education researcher randomly selects 48 middle schools and talks to all the teachers in each school. So there's 48 schools that they pick, and they're going to talk to every single teacher at that school, you know, throughout the U.S. There's way more than 48 middle schools in the U.S., so that one is a cluster. And on my next slide, we won't do them all, but you can pause the slide and see if you can recognize the rest of them, and then I'll show you the next slide. And here are your answers for those different ones. So once you get your sample, then you're ready to start going out and getting your data. It's super important that you get a sample that's representative of your overall population, because once you screw up your sample, there's no going back. You just got to throw everything out and start over again. The data is garbage. But if you do it the right way, and now you have data, we got to get it organized so that we can figure out all of these important things that we're going to talk about for the rest of this section. So we need to think about what kind of data did we get, and then what does that mean for what I can do with it. So there's categorical data. We will also call it sometimes qualitative. This textbook uses categorical. I usually say qualitative. Qualitative is much more popular, but really it doesn't matter because we're going to be talking about quantitative data, which is a numerical measurement. So categorical data or qualitative data is just like labels. Hey, what's your favorite TV show? What town were you born in? What kind of car do you drive? That kind of stuff. That's categorical. There's no numbers. Quantitative is a numerical measurement. How old are you? How far did you drive to work this morning? How tall are you? Stuff like that. How much did you spend at the grocery store? Those kinds of things. Now we can organize both of these things into something that's called a frequency distribution. I mean, you probably just ever heard of it as a table or a tally chart. Now the categorical one is really just a frequency table where the stuff with the quantitative is going to be a frequency distribution. It really doesn't matter to me how official these things are called. If it's a number, we use the term bins, where if it's categorical, we just say categorical. None of that really matters to me. What matters is that you have all of this data, you're going to organize it in a table. That table is going to be a frequency distribution. Now, the types of numbers that appear in that frequency distribution table can actually be one of two different types of numbers. You can have discrete numbers and you can have continuous types of numbers. So yeah, the weights of supermodels, the ages of respondents, those are numbers, that's numerical data. But I could also talk about those numbers being, how do I want to measure them? Do I want to measure them where I'm only talking about whole chunks? So I'm like, let's talk about ages, right? After a certain age, we don't say, I'm 42 and a half years old or something, right? Like I would just say I'm 42 or I'm 43 or I'm 44, where when you're a kid, you say like, oh, I'm like 3 and a half, I'm 3 and 4 months. So if you're going to use years so 3 years and 5 months, right? That's going to be continuous because there's all this space in between 3 and 4 that I'm like counting up and reporting. Where if it was discrete, if I'm just going to say, oh, they're 3, they're 4, they're 5. Same thing with supermodels. Like most people are not reporting their weights like, oh, I weigh 122.4 pounds or something like that, even though like if you get on the scale, it will say stuff like that, right? Where you have this. But most people don't report that. You say, I'm 112 or I'm 140 or I'm 210 or, so you would use those discrete values. How you collect the data and how you decide to collect the data kind of does depend on like which one you want to deal with. And sometimes you have a choice, but a lot of times you don't. And the most obvious one where you don't is for discrete, particularly when we are talking about for statistics, is people. You can't have 2.5 people, right? Like there's no continuous counting of people. It's 1, 2, 3, 4, right? That's discrete. If it's 1, 2, 3, 4, that's discrete. If you can have 2.5, 4.5, like 5.75, then it's continuous. So for the type of number, if you're trying to figure out something is discrete or continuous, say, can I have half? No, then it's discrete. If you can have half, it's continuous. People are always discrete. You can't talk to 3.4 people. Now, to kind of compound the number confusion, sometimes numbers are used as labels and then are considered categorical or qualitative. So numbers on your uniform, like you play a sport and your jersey number is 3 or whatever, you're not the third person on the team. It's not a ranking, right? It's just a number on a shirt. It's just a label. So it doesn't really matter. It doesn't represent anything. It's not a measurement of something. For you to be a numerical measurement, for you to be qualitative, it has to be a measurement of something where it's representative of quality. If it's just like a label of like that you pick, then it's categorical. So usually we try to avoid using numbers as a category. So instead of saying like person 1, 2, 3, 4, we'll say A, B, C, D, something like that. But we could organize all of that different type of stuff in a table. So let's say I have this categorical data. I have these records of grades for, this is the answers on a multiple choice test. So the first question on the test, and the 28 students answer it, and these are what they answered. Some people said A, some people said B, right? I got A, B, C, D, E. And I want to make a table. I want to organize this into a frequency distribution. So I'm going to create a frequency table. Don't overthink it. It's just a table. This is not going to look great right now. So this side is going to be your response, right? The thing that you're counting up. And then this one's always your frequency. How many of those things did you have? I got A, B, C, D, and E. Well, how many A's did I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You write that down. A B, I got 1, 2, 3 B's. Oh, did I? No, I didn't miss an A. 1, 2, 3, 4, 5, 6. 6 C's, but I missed a B down here. That's why I always cross it off as I go, because it's hard to keep track. D, no D's. 1, 2, 3, 4 E's. And that's it. That's your frequency table. You check to make sure you got them all. Does this add up to 28? Yep, that's my winner. Here's a more legible version. Right? You just write your responses. What are the things that can happen? They go in here in bins or categories or classes, whatever you want to call them. And then you just count up what you got over on the other side. That's it. You check to make sure that it works. You do the same thing for numbers. It kind of depends on how many numbers you have. So let's say I have a short group where I asked about how many how many siblings do you have? And these were my responses. I have 0s, 1s, 2s, and 3s. Oh, and 4 and 5. So I don't have a ton of numbers here, right? I got from 0 to 5. How many said they're an only child? How many have 1? How many 2? Right? And you just count it up, and then you check to make sure that you got everybody. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3 rows of 10 is 30. Does this add up to 30? Yes. Then I got a 1. Now, if you have multiple numbers in here, then that could be a little bit of a different situation, right? I have a short list, right? 0, 1, 2, 3, 5. But what if this went from like 0 to 2,000, right? We don't want a table with 2,001 rows. So then what I need to do is figure out how am I going to break this up, this 0 to 2,000, so that I can make what I'm going to call, and what Excel calls, bins. Most textbooks will also refer to them as bins or classes. So if I first want to figure out, well, how many classes do I really want to have to deal with here? So you don't really want less than 5 if you could have a choice, but you also don't want more than 20, right? You don't want something with 20, 30, 40 lines in your table. So like 10 is a good way to go. So let's say I want that to be 10 down here. So then I would take my maximum data value that I have in my set. My storyline was 2,000. And the minimum value, well, that was a 0. So and then I would just divide. And so that's going to give me a 200. This gives me what's called the class width. How wide do you want, how many numbers are going to be in that set? So it would be from 0 to 199. Because 0 counts as a number, right? 1 to 199 is 199 numbers, but I need to count the 0. That's actually my 200th number, right? And then this would go from 200 up to 399. And I would just work my way down the list. Now, this is like the right way, right? This is like the formula way. We play with it a little bit so that you can get something that's a little bit easier to work with. These were nice numbers, but you wouldn't want a class width of like 18.23 because that would not be fun to have to add up. But once you get that class width, then you set the minimum value for that lower class limit, which for us was a 0, and then you add that class width all the way down. So I had 0, and then it was 200, it'll be 400, 600, 800, right? All the way up until I hit the 2,000. And then I kind of look at where this lower class limit is on my second line, and I kind of just back that up 1. And then I add the 200 down for that, and I count it all up. So let's look at an example. This data is a little old now, looking to 2016, and it was all of the female Fortune 500 CEOs. So there's 500 companies in the Fortune 500, right? These were all the ones that had women as the CEO. I think there's 16 here. That's it. I think I couldn't do the top 100 because there was like 3 at the time. I think it's actually worse now, but at the time, for the Fortune 500 companies, out of the 500 CEOs, 32 of them were female. This is their compensation, is to the best that I can find with the resources that I had. And so you can see we're all in millions. Let's see, we have our smallest number. See if we got, I feel like it was a 2.2, I think is the smallest. And then our largest, was it not 53? Is it 53? Yes, it is. 53 million right here. That looks like it's our biggest. So I don't want to, that's 51 million lines, right? So I don't want to have to write 51 million lines. I'll say 53.2 minus 2.2. Maybe I want to have, I don't know, what do I want to divide by, like 6 or something like that? So I would have 51 divided by 6. And I'll take out my handy dandy calculator. on my phone. 51 divided by 6 is 8.5, which I don't want to be added by 8.5s. That's annoying. So let's just make it a 10. Now, yeah, I know what the rule said, but the rule is not like a hard and fast rule. You don't have to use 8.5 because that's what you happen to have come up with here. You can finesse that a little bit. So like even if it goes down to 6 or down to 5 lines, or it goes up to 7 lines in your table, that's okay, because we're going to work with adding 10s, and that's going to be a lot easier to deal with than my 8.5. I also don't have to start with 2.2 necessarily. I can just go ahead and start with 2 million. And then add my 10 millions down. So 2 million, 12 million, 22 million, 32 million. That's going to be a whole lot easier. If this starts at 12 million, let me back this up to 11.9. Right? Because after that, it would go up to the 12. And then this started at 22, so I'll say 21.9, and I'll work my way down. And I'll get something like this. So that these are my bins right here. And I just count up how many numbers fall in there. How many numbers are between 2 million and 11.9 million? How many are between 32 million and 41.9 million? Let's look at that one. So 32 million, here's one. And what was it, 41 something? Oh, here's another one. There you go. Those are the two. Those are the only two that fall in there, 1 and 2. And so that's my 2. The 2 million, 12 million, these ones right down here, those are called my lower class limits. So that's the smallest number that you could be to get into that class. So you got to be a 2 to fall in this first class. Nothing smaller than a 2, nothing smaller than the 12, right? That's where it starts. But it also has a top end. Right? Or else, because if I said just bigger than a 2, then you just got one class, right? Everything here is bigger than a 2. So that top one is going to stop on this side, and that is my upper class limit. So stuff that's between 2 and 11.9 inclusive, right? So I could be 2 million, I could be 11.9 million. You're going in this category right here. Now, what if you had somebody that made like 11.93 million? What do you do with them? Do you put them into this one, or you put them into this one? Those are called class boundaries, and those are things that you set. Like, what are you going to do with those in-between values? Most people round mathematically. So, if you make 11.93, I'm going to dump you in here because this would round to 11.9. But if you make 11.95, well, that's going to round this all up to a 12, so you'll go into the second class. So those are your class boundaries. Oops, I went too far. Those are my class boundaries. We're not going to worry about class boundaries that much. We will use class midpoints, though, which is just what it sounds like. It is going to be the midway point between these two numbers. So you're just going to take these two numbers, add them up, and divide by 2. And then you will get the class midpoint. Now, notice what's going on with these numbers. 6.95, 16.95, 26.95, 36.95. You see a pattern, right? 1.95, 11.95, 21.95. I didn't label the other ones. Let's go back. All of those numbers that I had labeled for my class boundaries and for my class midpoints, they all are using that same class width of 10. So, like, once I find this first one that it has a class, a midpoint of 6.95, I don't need to add these two up and divide by 2 and do the same thing here. I have one of them and my class width. Just add 10 all the way down, and you're good to go. So once you have these frequencies, I like to call these hard counts, right? Or you can call them a head count. How many of you make this amount of money? How many of you said A for question 1, or B for question 1, like that. That's the how many. You can also talk about things in proportions or with percents. So I can say, out of this group here, 4 people made between 22 million and 31.9 million, or I could say, oh, like 12% of the Fortune 500 female CEOs make between 22 million and 31 million, right? So you've heard stuff like that before. Like if there's 100 people in the class, or let's go a little bit even lower. Let's say there's 10 people in the class and 6 of them are boys. You can say 6 are boys, or you can say 60% of the class is boys. When you use percentages, those are either called proportions or a relative frequency. And you could do that even with ones that are qualitative or categorical. So remember our numbers that we had here, our answers, how many people said A, how many people said B, and we counted those all up. I could say, hey, 14 people out of this group of 28 students said A for the first answer, or I could say 50%. 50% of students said A, or 14 of them said A. 4 people said E, or 14.3%. How do you change a number to a percent? You just take that number that you counted up and divide by the total right there. You're going to come out with a decimal, so it'll be like 0.143, and then you just move it 2 spots to the right. So bing, bing. So 14%. With my Fortune 500 CEOs, 19 of them, I think, if I have the number right, were between 2 and 11.9 million. That represents 59.375% of the sample. So I can say 19 of the female CEOs made between 2 million or 11.9 million, or I can say roughly 59.4% of them. Either way is totally fine. If I use the head count, what I'm calling a head count, that's a frequency. Relative is just a fancy way to say percent. Which one you use, it depends on what you're using your data for, what's requested. One's not better than the other. But once you have your table and you have everything organized, you can start making some visual representations. And that is what we're going to talk about in 8.2. So you can make some charts, you can make some graphs, and then there's certain ways that you want to make these charts and graphs so that way, one, it's easy to figure out what's going on, but also that you don't miss by accident, make it look like something's happening that's not. So there's lots and lots and lots of graphs in the world, but most of them you know. So for example, the bar chart. You know the bar chart, right? This is bars going up, like this is the label down here, and then you say how many people have a hatchback, how many people have a minivan, or what percent. Either one of those is totally fine. So you can make a bar chart that talks about head counts or percentages. You can use a pie chart, although pie charts is always a percentage, and then you just put out to the side what it represents. So a bar chart could be either one. A pie chart is, or a circled graph, or whatever you want to call it, is always for percentage. One that you may be less familiar with, or maybe not even seen before, is called a stem and leaf plot or a stem plot. This is only for numbers. I kind of like this one, even though it's a big pain to make, so I won't ask you to make a long one like this. What you're going to do is you take your number and you kind of rip off the digit at the end. So let's say you got a 40 and a 42, right? You have right here. You rip off the little 0, and then you put it on the right one, the right column, and then you put the 2 next to it, and then you put it in the row that has the 4. This is your stem, and this is your leaf. So this is 40, 42, 50, 50, lots of 52s. Like down here, that's 102. That's 120, no, 102 and 104. I read it wrong. You don't see these a whole lot. They're easy to make. They're just ones that aren't used a whole lot. One that you probably see a lot, but probably think it's a bar chart, is a histogram. What's the difference between a histogram and a bar chart? Well, you can see that this is touching. These bars don't have a gap. That's because this is for continuous data, where my bar chart is either for discrete numerical data or for qualitative data, right, or categorical. Frankly, I don't care if the bars are touching or not touching. Like, that is not an important part of my life. But there is a difference when you do use them. Most people don't, lose sleep over it. But a histogram is for quantitative data only, and that data is going to be continuous, which is why they're touching. I'm going to go back. These are not touching because you can't have that gap in between. So like if this represents the ones, this represents the twos, you can't have 1.5. This is categorical, so you definitely, like, there's not a sports car, SUV, wagon blend. So no, they're not touching. These are touching because this is representing all these numbers in between here. Now, what you label the bottom with really doesn't matter, as long as you use the same thing every time. It could be the lower class limits. It could be the upper class limits. A lot of textbooks like the class boundaries. You can use a class midpoint. I don't care what you use. Just use the same thing for every bar, or use whatever they tell you to use. But there are some things that do matter, like what's going on with this axis over here. You can have a lot of misleading graphs, and you've probably seen a ton of misleading graphs. You don't want something like this right here because it doesn't have any y-axis. There's no labels. How do you know what this represents? You have to have a y-axis. And on top of that, you have to have one that starts at 0. You can't have something that starts at like 2 and then goes to like 32 and then jumps up to like 400. No. It's got to have a 0, and these intervals that you're going up have to be the same each time. So you can go 2, 4, 6, 8. You can go 10, 20, 30, 40, but you can't say like 5, 37, 119. You can't do that. How you make things from matter. So you can see that this is pretty messy. It's kind of hard to see where these would even land. Sometimes that happens anyway, even in good charts, is why you put that up at the top. But sometimes that's done on purpose with these like pictographs. So pictographs are a real problem, and that's why political cartoons use them all the time, is because they really exacerbate changes. So this looks way bigger than this, way bigger than twice the size, because it's not just bigger twice this way in the length, it's going to be also this way. And we know from doing area and volume that that is 4 of these, not just 1. If this is one of these little cigarette things looking in here, you would need 4 of them to make this picture. So that's a problem. And I got a big old mess on my screen, so let me clear off this ink. And then we have another one that's got colors, it's got no labels, it's just unnecessary. All of that's bad. So you don't want any of that. You want to make sure you always have an X and Y axis, that it's always labeled, that your y-axis always starts at a 0, and those numbers go up at the same rate every time, including percent. So you can do 5, 10, 15, 20%. You can't say 5%, 26%, 79%. That's not okay. And that is how you get all your data, make a table, and maybe put it into a graph.